So maybe I will start.
Okay, so welcome everyone to the Authentic School of Thoughts. Today's speaker is Professor Parvez from IIT Sarwar, and he will talk on Weibel's conjecture, Weibel's balancing conjecture, and its monoid element.
Yes, thank you, Maynard. So let me write down first my title, then I will explain. So my title will be a little bit changed. It will change because of my previous lecture. So previous lecture, we have missed something to say. So I am planning to say those things. So I will my title will be Weibel's vanishing conjecture. So am I audible, right?
Yeah.
Weibel's vanishing conjecture and Weibel's homotopy K-theory. Weibel's homotopy K-theory. So which is usually denoted by KH. So my plan is that, so as I already send out my abstract saying that I will discuss Weibel vanishing conjecture and my results with Krishna in that. But then the last lecture I realized that I am talking about Weibel homotopy K-theory, and some of from the audience pointed out that this is has not been discussed. So I will define KH homotopy K-theory and state some properties. So that is what is my plan. Okay, so this quickly quickly let me say where this KH appear. So we were discussing last lecture. So in the last lecture, so I was discussing mainly Horst conjecture. Horst conjecture, which in full generality is still open, but there are many results till now is going on. People are working, many results are there. But we mostly focused on the technique of CDH technique, CDH techniques developed by Hasselmeyer in the beginning. Then in the paper it is used by Cortinus, Hasselmeyer, and Weibel. But this is this technique is based on their another paper, Annals paper, which was with Celesting, where they proved Weibel's vanishing conjecture. So this using this technique in 2008, these people have proved Horst conjecture in some cases and Weibel vanishing conjecture in characteristic zero in both the cases. Celesting. Okay. So where they use like a K-theory in a model homotopy category using CDH topology, it's in CDH topology, its fibrant replacement is CDH fibrant replacement is actually, it was they have proved that started with the Hasselmeyer. This is actually Weibel homotopy K-theory. This is we are denoting by this is a spectra. This is Weibel's homotopy K-theory, and which is surprisingly was earlier defined by Weibel defined it in 1989. So this is Weibull's homotopy. I will define it today. Homotopy K-theory, which was introduced by Weibull in the paper which appeared in 1989. Okay, so it turns out to be very useful the homotopy theory, and it is very much used in the proof of both the cases, in Gauss conjecture as well as in Weibull vanishing conjecture. So based on this, I will divide my plan of my talk in two parts. Talk in two parts. So part one. So I will start with what I promised to say, like Weibel's vanishing conjecture. Weibel's vanishing conjecture, and say here what I will do. I will give a history, first history. It is now theorem, so I will tell you who is prove history and the history, and then this may be say part A, and in the part B, I will discuss my results. So I will discuss monoid analog. So I will define all these things. Hopefully, so I will discuss monoid analog. So this is our result with Krishna. Result with Krishna. So hopefully I will be finished it maybe 35 minutes. And then in part two, so in part two of my talk, so part two will be introduction to KH. And I will state some properties and we will prove some properties also. And it's some properties. Okay, so let's start with the part one. So a conjecture. So which is now a theorem. So what is the conjecture or vanishing conjecture? So part one. So this let me do it by like this. So he says that if you have a Noetherian scheme of dimension D, so let X be a Noetherian scheme of dimension D, then the result is, then the result can be during two parts. Part one is this negative K theory, KMX vanishes. This is zero, they are all zero abelian groups below the dimension M less than minus D. Like cohomological things. So, and part two is at dth minus dth spot, K minus D and X is isomorphic to K minus D X cross A to the power N. So polynomial extension with N variables. So this you can think of a Noetherian scheme over Z. So this is AN over Z. So this is according to my last talk, X is K minus D regular. So that is to say X is K minus D regular. So this is we have defined Ki regular. So Ki regular implies Ki minus 1 regular. But I mean after D both side vanishes. all of them both. It is k minus d k minus d minus 1 regular, but left hand side is 0, so right hand side is also 0. So after that, all of them vanishes with product with an also. Okay, so this is the conjecture, and then the now statement is the theorem is that it is true. So this is a theorem due to Maurice Kerj, Strunk, and Tamer. They have proved maybe 2017, it is published in 17. So it is proved in 16, 17 that the conjecture is true in that generality. So it is settled. Conjecture is true. So this problem is completely settled. Okay, so let me tell you the origin of the problem. So the origin is this all started with the work of Bas and Pawan Murthy. Their paper in Annals of Mathematics in 1967, they have done the calculation for curve. So for calculation, they did the calculation for curve. So it means that the dimension is more or less d equal to 1 or d equal to 1, but not in generality, some finite type scheme over field. So this is 1967. Then in 2001, so Weiwell in 2001 in his paper, this is also very nice paper. It appeared in Duke Journal of Mathematics. So there they prove if X is excellent scheme. So you can think of a finite type scheme over a field K. And d equal to 2. So he proved for nice surfaces. So his techniques also a little bit they are different. It's very nice technique. Okay, so this was maybe it appeared in 2001, but maybe he has proved in 2000 or earlier. Okay, so then with the invention of CDH due to Vovolsky, CDH topology and all. So in 2008, so here Cortinus, Hasselmeyer, Weiwell, so here will be system. Celesting, then this 4-author paper, they appeared in Annals of Mathematics in 2008. So their project started maybe in 2004-5. So we published in 2008. Maybe they have proved earlier. So they use they proved you can say that X is a finite type over a field K, where characteristic of K is 0. In characteristic 0 case. So this they have proved using CDH topology and CDH techniques. So my plan was discussing these two things, but to know these kind of things, we need to know the Weibull homotopy K-theory. Even if we discuss the proof, in the proof, the passes the vanishing K-theory passes to the vanishing of the Weibull homotopy K-theory, and characteristic 0. They prove that CDH topology, CDH descent and roll, CDA descent. So all these things I am calling CDH techniques. Okay, so this is in the beginning my plan to discuss this, but now I will discuss this Euler homotopy theory. But what for this is for characteristic zero, and then assuming then there is a Geiser Husserl in characteristic P. Geiser Husserl, they worked on characteristic P, and Amalando Krishna also. Both of them in different paper. They have worked on characteristic P. Then they're assuming strong resolution of singularity. They have some result in characteristic P. So assuming say, resolution of singularity. So let me not say strong. So resolution of singularity, as in resolution of singularity, they have some results. Resolution, they have some result. So you note that in characteristic zero, containing Q or in characteristic zero, this resolution of singularity is always there. So that also they take into account in the paper. Quaternius, Hasselmer, Celestin, and Weibel. They have some results. They prove some results. Okay, so in another direction, what happened? Like this. So there is another interesting result in this direction due to Sen Kelly. Sen Kelly, what he proved? Sen Kelly in 2000. Sen Kelly in 2014, he proved in characteristic P case in the characteristic is actually essentially a finite scheme over K, and say characteristic of K equal to P, assume it is positive. Then this K theory, this KIX, which is something of abelian group, and if you tensor with P inverted abelian group Z on by P. So after inverting P, he said that in a characteristic P case it is zero. So I less than or minus D. Okay, so this is more or less history about this oil vanishing conjecture and results. So what happens? Yeah. Okay, so now I will discuss my result with Amananda Krishna. So before that, let's say what is quickly say what is monoid. So let's say what is monoid. Now we'll discuss our monoid analog. So let's say what is monoid. So let M be a monoid. So let me say quickly what is monoid. So monoid is like we have a abelian group. It has a binary operation, and then in the axiom of the groups you have a identity element, associativity, and we will assume commutative monoid also, a closure property. Only thing we don't demand is that it may not have a inverse of every element, may not have an inverse. So by definition every group is a monoid, but every monoid may not be a group. So because we don't demand that every element has a inverse, and in our situation we'll be assuming a monoid to be commutative and cancellative also. So what do you mean by cancellative? See, so if you have like if monoid operation is, say binary operation is, if I denote it by plus, so like a plus b equal to a plus c should imply b plus b equal to c. So this condition is obvious if it is a group. I mean, you can just add minus a both sides. But if it is not a group, then it's not clear. So but we then, however, we demand this property to hold. We can cancel. So this is called cancellative. So the example to keep in mind is that, so you think of, let's say we have a polynomial ring with n variables. Say k is a field, k x1 to xn. So this is a polynomial ring with the n variable, and you take any monomials and take the ring generated by this. So that will be a monoid algebra. So M you can take it to be any finitely generated any monomial from here. So let's say you can take some. So maybe you can take, say, x1, x2, x1, x5, x1, xn, like that. So it is a monomial generated by this. Then somehow people make group ring. Then similarly you can make it a monoid ring, km. So this is a subring of k of x1 to xn, right? So you can make it a lot of monoid ring. You just take some monomials from the variable x1 to xn and make it. And this is commutative cancellative, because this monoid xn monoid generated by, so you can take monoid generated by with the x1 to xn. So this is like a free monoid. They do not have any relation. But if you take the monoid generated by, say, x1 square, x1 x2 x2 square, then they are not free monoid. They have a relation, like this into this is square. So you can take any monomials and take the monoid generated by these things. So you can form a lot of ring in this way. Okay. So then we ask. So instead of crossing with an, I want to cross with monoid m. So an means monoid, free monoid generated by x1 to xn. But instead of xn to xn, I want to cross with any monomials. Okay. So what we want to ask, then my question will be, then you want to ask whether ki of x is isomorphic to ki of x cross m. I mean, m means then you have to say over. So I can take, say, look, okay, let me write xm. So by xm I mean this is xm. You can think of as a so by this I mean you can take a x cross spec of zm. Okay, spec of the ring is the monoid generated by this. So this is my xm. Then I want to ask this ki ix is isomorphic to ki xm, whether it is true for all I less than equal to minus t. So this I want to. This is our question. In fact, this we prove. So this is our result with Krishna. So let me write down the statement. So earlier we proved in some cases in as a resolution of singularity. Now we wish that now we think we can prove more generally. So let me state our theorem. So this is with Krishna, and this is our theorem. So what we can prove it is that if let x be a Noetherian scheme of dimension d, then we can prove, and you assume m to be m is a, and we let's say assume finite element is not needed because K-theoy commutes with co-limit, but let's say m is commutative, cancellative, or maybe we can relax it, partially cancellative, but let's say cancellative monoid. I don't want to define partially cancellative. So then we prove that this ki of xm. See, you see, if we basically if they are isomorphism, ki by Karl-Strom term, I less than minus d, this is always 0. So this is will be 0. So that is what we prove. So this ki of xm is 0 for I less than minus d. Right? So this means that I less than minus d, these two are isomorphism. Because this is always 0. This is by Karl-Strom term. So we have proved this thing. But at minus dth level, we have to assume m to be semi-normal. If m is, so we should say further, assuming m is semi-normal. So we have this minus d ki minus d x is isomorphic to k minus d of xm. Okay, so any questions so far? So semi-normal means, so given a monoid, so one can naturally associate group completion of the monoid. So this is same group completion as it is done by Grothendieck. Like we started with finitely generated a projective model, you take the direct sum and then you take the group completion. So this is the same kind of group completion. So it is semi-normal means, so whenever if you take a element x from the group M and for x in the group of M, GPM means group of M, and whenever this x square x cube square and cube belonging to M, then you demand that x should be there. So this is called semi-normal. Okay, so but we must say that, so to prove this result, very strong input coming from this Goulart result of Goulart. So who actually proved that every finitely generated projective k module is free? So that is k naught of km is isomorphic to z. So it is weak way. In fact, he proved that every finitely generated projective k module is free. It's not a step. It is actually a free. Okay, and then there is a contribution due to Swan also. So Swan proved, that's why we say Swan actually generalized. He proved that K naught of R is isomorphic to K naught of Rm when R is regular. So this is based on Swan also generalize it with the idea of Goulart based on the work of Goulart. Okay. So once you have this, then if K naught of R is isomorphic to K naught of Rm, then one can quickly see that K minus 1 of Rm is 0. So for any regular ring, negative K theory for monod algebra vanishes. So let me give a quick proof of it. And so this is okay. So I was telling about input. This is on input coming from Google J and so on, and the second plus on input coming from a pro descent of pro. Let's not write so many things in on slide. And another input to prove our result is so another input other than Google one result. And not only that, then we use lot of monoid theory to reduce the result to a normal case. So there is a lot of monoid theory is used. So, but another generally strong results are like a 2017 result of Karj term. Another input is pro descent of Kurj Strung and Tamel. The result from 2017. So this the result we have used very strongly. So let me quickly say that for regular ring, negative K theory vanishes. So that will remind us the definition of negative K theory also. So what is the negative K theory is defined? It is defined in this way, right? So we have this is defined inductively. So we have this bus fundamental sequence, say K naught of R to K naught of Rx and direct sum K naught of R X inverse. So this is another variable, but I am taking only the inverse variable K of 1 by X. So it maps to K naught of, so this is exact sequence K naught of R X inverse, and then you take the co-kernel, and co-kernel is inductively defined as a negative K theory. So this is the co-kernel, so it is 0. Okay. So suppose I want to prove so let me write here itself. Suppose I want to prove a negative K theory when I say monodynamic K minus 1 of Rm is 0 when R is regular. Suppose I want to do this. So how do I do it? So what I have to show, I have to prove that K minus of Rm is 0, right? So let's say you take a so if I want to get K minus 1 of Rm here, I have to replace R by Rm, right? So let's take a K naught of Rm. So this is, then we have a map, like write down another bus fundamental sequence K naught of Rm and another variable X, and direct sum K naught of Rm. We add another variable X inverse, and then K naught of R M, and then we have a similarly a LoRa extension. And then we have a co-kernel to be K minus 1 of RM, which is going to this is because this is the co-kernel. But since R is a regular ring, this is an isomorphism, right? And if M is a monoid, see Mx is also a monoid. It is like M direct sum X. So this is monoid generated by M and X. So and R is regular. So this is the isomorphism. This is the isomorphism. So this whole thing is an isomorphism. So this is the whole thing. This is an isomorphism. And similarly, this is also a monoid. I mean, monoid is not you have to be a positive monoid. You can take the Laurent variable by inverse also. So this is also a monoid, and this is true. This is also isomorphism, right? So these all these things are isomorphism. This says that by 5 lemma you can say this is also isomorphism. But for a regular ring, this is 0. So this implies that this is 0. So it is basically the result of Goulart-J-Swan. From Goulart-J-Swan for the negative K-theory of monoid algebra vanishes. But we generalize to first we smooth the scheme. So then from a smooth scheme to any scheme we go by some sort of descent theorem, co-descent theorem, but then we remove the condition of the smoothness, and then we go to the minus D level. There we use some spectral sequence argument. So here I will stop about this vanishing thing. If you have any questions, let me know. Now onward, I'll move to Weibull's homotopy K theory. I shall define it and discuss it. So any questions so far?
Yes.
Menak, any question, or I will move to homotopy K theory?
No, I have no
Okay,
questions. If any of the participants have anything, they can ask.
So let us move to Weibull's homotopy K theory. Let's give me the quick introduction. So this is some sort of homotopization of K theory. So this will be denoted by spectra is denoted by KH. So how this spectra is constructed? So let me quickly construct it, quickly define it, and then we'll say some properties. See, so from this negative K theory, you saw that how the negative K groups are defined, right? The K minus 1 are. So in that way, one defines this spectra level. Spectra level. So K of, so let's say, let me do with a ring level. So K of Rx. Okay, so K spectra on the ring R, you take the direct sum K of Rx inverse, and then there is a map to K of R X inverse, and this co-fiber is denoted by L K of R. Okay, this is the this is co-fiber of this map. So this is LK of R. From there, negative K theory are defined. So then we have this loop space omega K of R X inverse to. So you will take the loop to both sides. So this will give a map from omega L of KR. Okay. And this for this you see the Weibull's book. From we have a map from K of R to this omega K of Rx X inverse. This is some cap with X. We have this map. So composition will give me a map like this. So what we have got is that K of any ring to map from K of omega L of K of R. So omega KL is another space. K is a space. So omega L K we have constructed, and then we have got a map. This is the composition map. Okay. So we can apply the same method to omega L K R. You think of it, this is an spectra. Then we will get omega L of omega L. So that I am denoting by omega L and again omega L. So this is omega L square of KR. And you can keep doing this. Okay. So if you keep doing this, this will denoted by, and this is if you do this, then the whatever the okay. So let's write down in this dot, and you take the homotopy limit. Just let me write down nicely. That's not very. So this you take the. I want to take the limit, but so this is all are spectra, so better. And this there is a model structure. This is the homotopy category. So you take the homotopy limit, whole limb. Okay, whole limb. So you take the whole limb along this. Okay, and this the whatever the things you get, that is actually said KB. This is pass non-connective spectra. So Quillen KR is the connective spectra. Means you can define pi 0, pi 1, pi 2 in this way. And here you can define pi minus 1, pi 2. So the negative K theory is defined. So this spectra, non-connective K theory spectra. So it means that negative K groups are also there. So this is a non-connective spectra. So this KB, this is called non-connective. I think this you must have seen earlier also. So okay, so from here, so we'll define this Weibel homotopy K theory. So now what we will do now? So given a R, we will consider this delta R. So delta, what is delta R? Delta is a simplicial ring. Simplicial. So let's see the structure of the ring. So what is delta R at nth position? So this is R T0 to TL. So n plus 1 variable, and then you go modulo sigma Ti, this hyperplane minus 1. Okay, you go modulo this. So this is so this you take this ring. Nth step, this is the ring. So the simplest ring means a sequence of ring. There is a face and there is a natural face face map, and face and degeneration maps are there. Okay, so you take that this delta of R. Then what we'll do? Okay. So each level you apply this by non-connective K theory, KB of delta R. So you get a sequence of spectra, and you take this geometric realization. It's called fibrant geometric realization. Okay. So this whatever the geometric realization, that is another space spectra you get. Okay, so this is a sequence of spectra. So limit will be another single spectra. Okay, so this is done in a degree way. So this will denote by, this is by definition KH. Okay, and this KH I of R is pi I of this space. Fiber geometric realization of this. Okay, so this K theory, this homotopy K theory, I have defined it. Homotopy K theory for this is for rings, right? And this is for any rings, associative rings also. Need not be commutative. But and then in this paper, in the paper of Weibel, what he did is that from ring he defines for a quasi-positive scheme. So this I will not discuss. So this he is defined for quasi-positive scheme. So here main technique is, and the idea is here technique is to use something called a Jonolu device. J-O-U. I don't know, so let me write down the names correctly. Jonolu, J-O-U. Again, the N. Then M, Jonolu, N-O. LOUS, something called journalist device. So this is taking the affine vector bundle, and then you take the quasi-positive scheme, taking the cover, affine cover. You can go there. But then after that, from quasi-positive scheme to general scheme, he is going. So there he is using this. So they using this he defines. So this is defines KH here. Okay. That from now from quasi-positive scheme to general scheme, to go to general scheme. So for this he has to prove something called check descent. Let me write down. So here he uses some check cohomological descent, which he proves in the paper, and then he defines it for check cohomological so cohomological descent. Okay, then so finally, homotopy K theory is defined for any scheme. So one can do vanishing, or can ask the question for vanishing, the same question for homotopy K theory also. So this is being also done. This is also proved by more generally, I think, by Kajis to Ultraman. So in that invention paper. Okay, so yeah, so this is the definition. So now, so let us state some interesting properties, and let us see some of the arguments also. So some properties. So let's write down so whatever the K-theory properties are there, this homotopy K-theory also enjoys similar properties. So first thing in the nature is that, so I will write down those properties mostly for the ring, and most of them generalize to all schemes. So first one is homotopy invariance. So what is it? So it means that this KH I of A is isomorphic to KH I of A xn. So you can take any free group also, xn to xn, commuting variables for all n greater than equal to 0. And this A can be any associative ring also for any ring. So, but here see in the case of a K theory, it is true for regular, but in the way it is constructed, so these things, the delta, the T0 to Tn, you can think of this adding n variable, and forcefully they are making it kind of, I mean, in the definition itself, they built in such a way that this holds. So homotopy, but it holds for any ring. It need not be regular. That is the main point to remember. And I'll discuss the proof also. Proof is also very easy. So I'll discuss the proof also. Part 2 is a fundamental theorem. So fundamental theorem, fundamental Ajax theorem. So like K theory, fundamental. So what is the fundamental theorem? Fundamental theorem is saying that if you take a KH for any group, KHI of a lower polynomial, it splits into two groups, direct sum. So it is like KHI of A, direct sum, KHI minus 1 of A. Okay. So there are many other properties. So before yeah, so there are more properties I will write down. Before that, so let's see the sketch of the proof. So which will already, so that we will see how the definition being used. So I want to say that so it is enough to do for one variable, right? Because A is anything. So enough to prove KH. In fact, it is two homotopy KH of A is isomorphic, same as KH of AX. Okay. So, but how do you see this? This is easy because so what is happening? So you take the delta A. So from A to delta A you go, and you take the delta AX. So in these two rings, simplicial rings at x equal to 0 and x equal to 1. So because when we take the simplicial ring, then we pass it to the homotopy category, right? So there is a so these are this and this are homotopy simplicial homotopy equivalence. I mean, there is a homotopy exists between this and this. Simplicial homotopy equivalence of rings. So spectra will be same. So roughly this is the idea, equivalence of rings. So spectra will be same. Okay, so this is the roughly this is the idea that each level they have their simplicial rings are same up to homotopy. Second thing is that so this also holds a spectral level, is fundamental theorem. So this is some sort of looping is so how does it work? So let us recall fundamental sequence for K theory. So I already wrote down. So again let me write it down again. So before I write, I need some space. So let's erase this. So let's write down. Let me write 2 here, and then from here, let me write down the fundamental sequence. So this is true for all n, right? Kn, Kn, Ax, direct sum, Kn, Ax inverse to Kn, Ax inverse to K minus 1 of A. This is to 0. So now what I'm going to do, so you go modulo these things. So you can go modulo these things in a space. So this is true for all n, or n belonging to J. So I will write down this as So instead of write n, so you write k of ax and take the cofiber with k of x inverse and go modulo the cofiber. So still, so still then we have a map to this k of ax inverse. Right? Because this is the anything coming from here is going to this. In spectral level also it happens. So and what is this k minus 1? So this we'll write as a loop space. So, right? So this is so k minus 1 will be given by omega inverse of this k. Okay. So this is homotopy fiber. Okay. So what do we want to prove? We want to prove that yeah, so you replace everywhere by kh. Then what do you see? So you replace it and okay, so this apply everywhere kh. Okay, so this also you keep this. So go modulo ka. Now replace k by kh. So if you replace k here kh, what happens? This is kh. So then this is equivalent to homotopy equivalent to weak equivalent to point, right? Because we have seen that in the part 1 this is their isomorphism. Similarly this also this becomes point. So this becomes a point. So okay, so if we replace, if you add kh, this becomes a point. Okay, this is kh, this is kh, and this is kh. Okay, so once this becomes a point, so it means that so if this, so the point cross point, this is a point. So this implies that and this is the cofiber. So this implies that this is weak equivalence. So it means that we have a spectral level kh of a. So this implies kh of x inverse is equivalent to kh of a direct sum the omega inverse of kh of a. So if you apply pi I both sides, then you will get khi, and this will be khi minus 1 by definition. So this is how the proof works. So basically, it follows from this fundamental sequence and using the homotopy invariance property. So this is the fundamental theorem. So there, let me write down now some more properties. So let's see. Some more properties. So another interesting properties is that, so there is a spectral sequence. So let me write down this as a theorem, spectral sequence theorem. So there is a, so there is a right half plane, the homology spectral sequence, right of plane homology spectral sequence. Homology spectral. So all these things are due to Weibel. So Weibel homotopy paper. Okay. So this is this theorem. So all these properties are Weibel's results. Weibull has a paper on called Weibull's that algebraic homotopy K theory. So here this E1 page, homology index, homology index E1 PQ is equal to NP. This NP we have defined last lecture. This interestingly, this connects with the K theory way of ring with that is converges to KH of P plus Q of. So this is this is a connection with the Quillian K theory to Weibull's homotopy K theory. Okay. And so let me say, but this is also clear, right? So it is clear that we have a map from K to KH. Right? This is just almost by definition, because the way it is KB are defined, right? KB of something, and then geometric relation is taken. So we have always this map K to KH. And then what we have is that, okay, so yeah, there is another interesting theorem. Let me write down. This is called something called excision. So excision theorem will say that let A be a ring and I an ideal in A, then there is a homotopy fiber sequence. Then we have the following homotopy fiber sequence. So KH of I to KH of A to. So KH is defined for any associative ring, even for non-unitary. It makes sense. The same definition. So KH of A mod I is a homotopy fiber sequence. Is a homotopy fiber so this means that this means that there is a long exact sequence. There is a page. There is a long exact sequence as follows. So we have write down the long sequence. A H say n plus 1, so it is going from here to A. If you have a mod I, then it will map to KH n of the ideal, which will map to KH n of A, and then this will go on. This helps us to calculate some homotopy K theory. There is one more, so let me make another interesting. There is another interesting result, another proposition which connects K theory, so which connects with this Sen-Kelly's result, and so which will reduce Sen-Kelly's theorem to prove some vanishing of Weibull homotopy K theory. So if you see the following theorem, that there you will see the connection. Let A be a ring, and such that L is an integer, such that 1 by L belonging to A. So L is an integer, non-zero integer. That's the 1 by L belonging to R. And then we have this K star of A. So K theory of ring A with Z mod L coefficient is isomorphic to homotopy K theory of A with Z mod L coefficient. Yeah, where so let me say what is this, where K star of A Z mod L, and denote the mod L, denote the mod L homotopy homotopy groups. So there is a classically in topology, there is a homotopy groups, and then if you have any abelian group, and then there is a homotopy groups of a space with the coefficient in the abelian group. So this is how these things is defined. So similarly for the KH also. Similar definition for KH is also there. Similarly for KH. Okay, but then why this K theory with coefficients and K theory without coefficients? What is the connection? So that is the connection is, so let me write down as a, let me say as a remark, as Weibull says, universal coefficient theorem. So here also there exists a universal coefficient theorem which connects K theory with coefficient with the K theory of a ring. Universal coefficient theorem. So what is the universal coefficient theorem? It says that it says 0 to we have the following strategic sequence: Kn of A tensor Z mod L to Kn of A with coefficient in Z mod L goes to, and this goes to tor of Kn minus 1 of A, comma Z mod L, which goes to 0. So this is called the universal coefficient theorem. Okay, so which connects K theory with coefficients with the K theory with exact without coefficients, but taking the tensor product. So this let's say this proposition 1. So proposition 1 actually will give you how the proposition 1 sketch. So I will just give a sketch of proposition 1, a sketch of proof of, because this just follows from the spectral sequence. Proposition 1. So that those who know how to calculate the spectral sequence, it just follows from there. So what we have this following spectral sequence also, with homology spectral sequence. So U1 page is NP KQ A semicolon Z mod Z mod L, which converges to, for the coefficients also we have this KH P plus Q A, whatever K theory of A with Z mod L coefficients. But then one notices that for a K theory with coefficient vanishes. These things, this vanishes. NP So this one can check. One can check that this NP of KQ is with finite coefficients. This becomes 0 for all P10. Then the result follows. Then the result of so what it says that then one can say that this star becomes isomorphism. K-theory and homotopy K-theory. Only P. Yeah. So I will stop here. So if you have any questions, you can ask. Okay. So I'm trying to stop here. Are there any questions?
Thank you, Professor, for the wonderful lecture. Are there any questions from the audience?
I should say thank you. Because we are patiently listening. Okay, sir. Okay, then. So this is my 2 talks. Hopefully, in the future, we will meet again.
Yeah. Okay. Send me the notes.
Okay.
And by the way, I
Yes.
just wanted to say that in the beginning when we decided, we actually had a different plan. Maybe you said something else. Like earlier when we decided, it was about your proposal for the lecture was something else. I think it got changed
Yeah,
after
K-theory.
we.
I was thinking about defining K-theory, defining K-theory of schemes and all those things. But I saw lecture I was going through, but then I saw that there are a lot of various people have already defined it. K-theory of schemes, K-theory all-Hausen category, in terms of class construction, all those things are there.
Yeah,
And
yeah.
properties there. So then I
So
thought
in
that
the
let us see some applications.
yeah, I mean this was nice anyway. Uh, I mean, the difference is just that you said you'll be discussing some abstract blow-up square and
Oh
use
yeah,
them
yeah.
to.
Actually, yeah, abstract global square I did define in my first talk, and that is used. That is actually a part of one of the core for CDS topology. So that I have
I see.
explained in the lecture 1 to
Okay.
prove this Horst conjecture. So this is needed for this much. This also for vanishing also. But I realized this viable homotopy theory nobody have discussed. So I just I
Yeah.
thought because eventually to prove the vanishing one has to pass to the viable homotopy theory. There because the CDS topology is locally smooth because after resolution of singularity and then in a smooth, if actually a smooth scheme, then K theory and homotopy K theory are same. Then one can work with homotopy K theory. So
I see.
one should know homotopy K theory and its properties to conclude anything.
I see. Okay.
So I changed my plan to discuss to say something about homotopy K theory. But I think it is good in a way that nobody have discussed it, and I said gave some introduction. So it is there already. People, all graduate students. I hope it will be useful for them.
Yeah, certainly.